Hi everyone. Welcome to our next session of ShaderLab Bootcamp. Hope you guys had a great time with our ShaderLab last time we spoke. So today we are going to be talking a little bit about what transformations are and what transformational matrices are in the context of game engines. This is going to really help you. If your intention is to build something from scratch, if you would like to build if you would like to work on a gaming engine and you would want to understand how things work under the hood, or B, if you just want to make a game and if you just want to understand how things move around. So this is going to get you started in terms of what a basic transformation looks like. And trust me, you're going to be using transformations everywhere whenever you make games, whether you're doing simple 3D, whether you're making games, you're going to be using transformation. So the way we have organized today's session is very much like earlier. It is going to be comprising of we are going to start with some amount of theory behind transformations, which I'm going to be taking up. And once we understand that theory, once we have a grasp on that theory, Videep is going to take over and he's going to be telling us about how to achieve that practically. For all purposes, we'll be using Unity as our engine because that's one of the most popular ones. So Videep is going to demonstrate on how whatever we learned today, how is it applied into a practical environment when we work with Unity. So before we go ahead, let me just quickly give you. You guys already know us. My name is Girish Sarwal. I have Deep Mishra with me. We both of us love 3D programming and gaming. In case any of you want to connect us with us, our Twitter handles and our LinkedIn profiles are on the screen. So let's just move ahead and let's dive deep into what transformations are. Before we understand transformations, let's really understand what 3D objects are. So on your screen, what you see are a few 3D objects, and this I kind of stole this slide from a last presentation, with the exception of an extra cube here. So the cube really helps us. I like to call this a ubiquitous cube because it really helps us understanding a lot of 3D concepts, and it's one of the most primitive 3D objects that you would ever come across. So when we talk about 3D objects, all 3D objects that we see on our screen are essentially laid out in a form wherein they comprise of corners like these. So if this orange dots that you see are corners, and if you look carefully in all the images on the right hand side, you would still be able to spot those corners. These are essentially points in 3D world that come together to bring up to create a 3D object. So if you look at the bunny in the second picture here, you would see that it also comprises of these little corners that come together to form a surface. If you look at the torso of a man and the head, you would see that again it has corners. They are very fine, they're very refined, so it really doesn't give you the feel of a corner. But essentially, all of these corners are typically what we call vertices, or a single one is called a vertex, and the set is called a vertices. When these vertices come together, they form something known as a mesh. So mesh is very much like a jali in Hindi, if anybody understands Hindi here. So it's very much like a jal. It's a net of these vertices coming together and forming a surface. If you look at the last one, which shows the terrain, you would again notice that there are a lot of corners or points in there which come together, form a big graph, and they form a mesh. They form a net of vertices, which gives us the effect of seeing a 3D object. So it basically forms the surface or the hull of that object. So when we really look at our ubiquitous cube, you would realize that we have the vertices which we just discussed. A single one is called a vertex. When two vertices come close to each other, we call that an edge. So what you see here is essentially an edge. And when three or more vertices come together, we call that a face. A face essentially is a single plane. So if you look at these four vertices, you would see that this is something that we would call a plane or a face in 3D terms. So The reason why we choose that number 3 here is because three vertices together can form a plane. 3 is the minimum number of vertices you need to form a plane. So you can make a plane with one vertex, you can make a plane with two vertices. The moment you have 3 vertices, you can really start seeing a plane. And essentially, if you look at geometry, a triangle is the smallest unit of a smallest polygon that can define a plane. So which is why anything that's above three vertices together, we call it a face, and all three plus faces get converted to triangles. So a face could really have, you could have 5 points in one plane that would define a face, but essentially when it goes to the graphics card, it would get converted into triangles. And this process is something we call as tessellation. So tessellation is something that the graphics card do by themselves. You don't really have to worry about that. But essentially what you have to understand is that all 3D objects look like this. All 3D objects are made up of vertices, faces, and edges. The reason why we need to know these terms is because these are going to be used very commonly when we're talking about stuff. So it's easier we figure that out here. So in your in your data set. So the only special case with graphics programming is that all these records essentially, or all these data points, are either made up of 2 values or 3 values. So each vertex can, in the two-dimensional space, if you're doing 2D work, then you would typically define a vertex or a pixel as a X or Y. And versus in the 3D domain, if you're working in 3D, then you would typically also add a Z coordinate to it, and you would typically define one data point or one record as a set of X, Y, and Z. Now, we also have to understand that these values are often dependent on each other, and the moment you change one value, it might have an effect on the other value, etc., etc. So they need to be processed and kept together. So they need to be processed as a single unit, and they need to be processed. They need to be kept together always. So the X, Y, and Z always stay together. So in the cube that you see, each vertex is defined by that set called the X, Y, Z. And as a matter of fact, today's processors or today's GPUs are optimized. In fact, if somebody goes back 20 years into time, when the Intel MMX technology came in with CPUs, in fact that's 30 years old, I guess now. So MMX essentially, which was known as multimedia extensions, was also a way of telling people that this processor can actually run parallel instructions on adding vectors and working with vectors. This was essentially built upon a technology called SIMD, SIMD, single instruction multiple data. And if you guys get some time, just have a look on what SIMD is on Google, and you would figure out a lot of things. But the bottom line remains that data in vectors essentially gets processed together. So you would typically make 2 vectors, and then you could add them, you could multiply them, you could do a lot of things in them. So when we keep X and Y together, we typically call it a vector. It is also essentially nothing but a one-dimension matrix. So if you look at this particular value here, this is nothing but a one-dimensional matrix. So if you go back to your high school maths, you will realize that a matrix is a set of numbers that's arranged in a certain format, and this looks very much like a matrix. Also, interestingly, if some of you are coming in from the artificial intelligence domains, you would have come across the word tensor. So essentially, a vector is also nothing but a one-rank tensor. So it's basically a set of numbers kept together, and that's how we typically represent geometry. The reason why we do this is because, like I mentioned, they need to be, these X, Y, and Z need to stay together at all times. So it really helps to keep them together. At the same time, there are other features inside a 3D development environment where you would like to keep data together. For example, color values, normal values, or maybe refractive indices, etc. You could have different values of this for the X, Y, and Z domain. So you would essentially want to keep them together at all times. So, talking a little bit, we our theory classes under our theory discussions today really would be about what vectors are and how do they really help us. So, for your understanding, you just have to understand that a vector just has it's a value that has a direction and a magnitude. If you know a little bit of trigonometry, you're really going to be having lots of fun with vectors. And the trigonometry that we typically use in rendering, in 3D rendering, has more to do with circles rather than triangles. It sounds a little counterintuitive, but you will understand why because we use a lot of sines and causes and all those mathematical transformations. So the trigonometry that we really see here is more about circles rather than triangles. So minimum things that you really need to do for 2D manipulation are things like need to understand what vector direction and magnitude are. You need to understand what is adding, subtracting, subtraction of vectors. You need to understand what is scalar multiplication, dot product. All these things are really available on the internet. I would really urge you guys to go and have a look at it. I mean, these are essentially these are keywords that you might want to search for on Google. So, okay, this seemingly is my favorite slide. And what is essentially a transformation? A transformation essentially, this slide kind of really defines what a transformation looks like. A transformation is you have a certain set of data and then you apply a mathematical calculation on it and you change that data. So anything that affects the geometry or the space or the orientation of any model or a mesh or a vertex or an edge or a face is a transformation. There are essentially two broad categories of transformations. One is the affine transformation, another one is the non-affine transformation. An affine transformation is something in which after you do the transformation, all the edges remain parallel to each other like they were earlier, or they remain at the same orientation with each other. So if you're translating an object, the first example that you see is where translation happens. The circle gets translated, so the circle now looks a little bit away from the rectangle. Or you could be rotating an object. So if you rotate an object, you could be rotating it around a certain axis, and the shape of the object doesn't really change. It is still a square on this side, but it is just that it has moved in its orientation. And finally, scaling is wherein you increase or decrease the size of an object, the overall size of an object, or the overall size of the object that you've loaded on the screen. You basically either increase it or you decrease it. When you increase it, you say it's scaling up. When you decrease it, you say it's scaling down. You could either scale an object uniformly around all the three axes, or you could scale it non-uniformly. All of these are essentially examples of affine transformations. Non-affine transformations, on the other hand, are things like skewing, perspective, or projection transformations, wherein you actually change the parallelity of the lines that are going to be drawing up that object. So common transformations in 2D, like we discussed, are translation, rotation, and scaling. Finally, we're going to be talking a little bit about 2D here, but the same things apply to 3D, and we're going to be talking a little bit about 3D in the upcoming slides. But this is basically to give you a jump start into what transformations are. So transformations essentially either they will change the position of an object, or they will change the orientation of an object, or they will change the size of an object. These are the primary three transformations that we always look at when we're talking about game engines, game development, etc. Common transformation in 3D. So if you're scaling down something, then essentially what happens is that there was a vertex here. So if you consider this as the ubiquitous cube that we were talking about, you take a vertex here, and that vertex gets moved to another vertex here. Now this entire object could be at the same position at the origin, or it could be translated. So when you translate, the vertex essentially moves from one place to another place in 3D space. And now imagine that if you did this transformation for all these 8 vertices that are here, what would happen is that you would end up with the entire cube moving to a different location. So if you look at this translation carefully, and if you imagine that all the corners or all the vertices on this were these were moved in a certain direction by a certain magnitude, or an operation was applied onto it, it would essentially end up being into another position, but it would still be the same cube, just that it will change the position or it will translate from a location. People who are coming in from HTML5 or CSS side, they would really be able to understand this very well. We have all these operations available in CSS. So we have scaling, we have rotation, we have translation. All of these are available, and essentially these are the basic transformations that you're always working with in 3D. So the order of transformations is essentially very important, and we generally follow the scale, rotate, and translate in that order. But you are free to choose any order. The only thing is that when following, if you're following one order, you might just want to follow that order always. You should not really be changing horses in midstream and doing any transformation at any time, because the end result can have a lot of impact. And why that happens, we're going to be discussing in a little while. But this slide should give you a basic idea of what happens, if I do a rotate followed by a translate, or a translate followed by a rotate. So the end result can really change. In this particular case, there was a cube that you first rotated. It's still a cube in a different orientation, then you translated it. But in the second example, you first translated and then you rotated it. So when you rotate, things really happen around the starting point. So you would end up with two very different results. So the idea is that if you're going with a certain amount of translation steps, you should always typically be following those translation steps. So we saw how we represent geometry. We are now going to be also discussing a little bit about how do we represent a transformation. So just like geometry, which was being represented by a set of vertices or a set of vectors, since vertices are those vectors, we need to process every vector. If we go back to this slide, what we realize is that each of these vertex is being represented by a vector. So what we need to do is we need to make some changes to this vector. We need to do a mathematical calculation on this vector and still get a vector out of it. So the way we do it is that since vertices are vectors, we need to be processing a vector and we need to get back another vector out of it. So if you go back to mathematics, we realize that there is a certain constant called a matrix which allows us to do this. And the way we do it is that if there is a matrix that's of size A into B, if that is multiplied with a matrix of size B into C, we get a final matrix which is of size of A into C. So imagine that if our vector was XYZ, which is a 3x1 vector, or if you look at it in a column format. So if our vector looks something like this, maybe in X, Y, and Z, and if you multiply that with a 3 cross 4, sorry, I think I made a mistake here. If you multiply that with a 3 cross 3 matrix, you would get a 1 cross 3 matrix, which again looks exactly like the vector that you started with. So when we apply a transformation, what we essentially do is that we take up a vector, we multiply it with a matrix to get a vector back. So let us say this was a column major vector. We multiply it here we are multiplying it with a special kind of a matrix called an identity matrix, which basically does nothing. So what happens is, if you go back to your basic mathematics, you would realize that when you multiply these two values, what you get back is the same value. So you would still get a vector that is 1, 2. In the second case, what we did was that we took a vector of 3 components. We multiplied it with the identity matrix, which is of 3 components each, which is a 3 cross 3 matrix. And what we got again was a 1 cross 3 matrix. Now this one, I'm doing a scalar multiplication here. A scalar multiplication is essentially wherein we can pick up all the elements inside the vector or inside the matrix and multiply it with a certain value. So when we do this, we get a result of 2, 4, 6. This is all basic mathematics. You will get it in all most of the books available. However, the objective here is to understand that when we are working with 3D graphics, you would be coming across with a lot of matrices at all times. So the nature of matrix multiplication is such that it is very well suited with when we are doing vector calculations. And essentially what happens is that if we look at at times what we do is that there is a special thing with matrices that we leverage. And the special thing is that if you're multiplying a vector which has two components with a matrix which has two components, there might be uh, certain items that we would like to store for the moment, or at the same time, there might be certain components which need to be applied as an extra operation on the vector. So what we do is that when we go with a one by when we are working in 2D and our vector has two components, we essentially try to multiply it with a 3 cross 3 matrix, because the extra row and extra column help us do a lot of operations that we would not have been able to do with a 2 cross 2 matrix. So as a rule of thumb, you would typically realize that when we are working in 3D, a vector would have three components. So essentially, the matrix is not going to be a 3 cross 3, it is going to be a 4 cross 4 matrix. And if you're working in any 3D engine, you would typically realize that the actual matrix that gets multiplied internally is a 4 cross 4 matrix and not a 3 cross. This also gives us a side benefit that when we are working with projection matrices, we can use something known as a homogeneous matrix. A homogeneous matrix essentially specifies that the components of that matrix that we are using are pre-calculated. They have all the calculations applied on them. So you could essentially think of them as you could think that all that extra row and extra column that we pick up with matrices, that helps us in one, storing some kind of temp variables, B, storing some properties about the matrices, or C, it also helps us do some extra calculations on the basic data. But all in all, what we have to understand is that transformations, whether affine, non-affine, or any kind of transformations that we discussed, are represented by matrices. So the general rule of thumb is you take a data point, you take a transformation, you multiply that data point with the transformation to get a new data point. So let's talk about a little bit about vector maths, and we'll see examples of 2D vectors here being multiplied by 3 cross 3 matrices. So in this particular example, let us say there is a point or there is a vertex in 2D space which is at 10 cross 10 comma 10. So x is 10 and y is 10. So like I mentioned, we would be representing that in a vector that has three fields. We would have an x, we would have a y, and we would have an additional item that we're going to be using for keeping some other data about this entire calculation. We multiply this by a 3 cross 3 matrix, wherein the which the top two look like this. Looks the sum this sub matrix looks like an identity matrix, and the third one, these are the columns where we're keeping that extra data that we need to do the addition. So when we carry out this multiplication using the laws of matrix multiplication, we end up with a vector that looks like 20, 10, 1. This is very similar to the main vector, but the point x has been translated by 10 points, whereas point point y remains the same. So when we apply this kind of a calculation onto a vector, we get a new vector which has the new coordinates. What we have to remember typically is that translations can affect the magnitude and both the direction of a vector. Similarly, we could do a rotation. So a rotation almost always affects the direction. It never really changes the magnitude of a vector. And here is when I said that it is more about circles. This is a simple example of how we typically carry out a rotation in 2D. Essentially, your original point was 10 by 10, and you create another matrix here, which is the transformation matrix, which takes the so let us say you were at 45 degrees at to start with, and you wanted to go to 60 degrees. So difference here, the theta here is the angle here is 15 degrees. So essentially, you would do a you would build a matrix like this, and there are mathematical rules behind this. We could discuss all of them in maybe another lecture, but there are mathematical rules about why this matrix looks like how it looks like. So the end result is that when you actually multiply this vector, the x gets changed to the x gets changed to x cos theta minus y sine theta, and the y gets changed to x minus x sine theta and y cos theta. So when you do this, when you carry out this calculation, what what you end up with is that this point 10 comma 10 moves to another point, which is xy in this case, and that's how you perform a rotation. Now imagine this particular rotation happening on all the 8 vertices of the cube, and your cube would actually rotate in the space. So that's how we achieve rotation. Now this is rotation in 2D. When you do rotation in 3D, you actually specify three different matrices for the x, y, and z axis. And if you're going down the route of an arbitrary axis, then that entire matrix changes. However, ultimately, when you're working on 3D programming, you will realize that ultimately we're going to be using quaternions to do that. Now, similarly, we can do scaling in a very similar fashion. You take a matrix and you multiply it with a vertex to get another vertex. Now you apply this entire calculation onto the entire object, and the entire object gets scaled. So these are fairly straightforward. When you do uniform scaling, that definitely affects the magnitude of a particular vector. But the bottom line still remains that you need to understand a bit of vector mathematics to do all of this thing. And when we go into the practical session, Videep is really going to help us. Videep is going to show us all of this in action. So things are going to get better. Things are going to get a better perspective. So once we have our transformation matrices ready, like we discussed, all transformations are nothing but matrix operations. When we are working with 3D, we use a 4x4 homogeneous matrix, and it's like whether you're working with color, whether you're working with vertices, whether you're working with normals, essentially there will always be a three component vector. So they're always going to look the same. So essentially what happens is that the actual matrix that you multiply it with is generally a 4x4 matrix. Now the idea here is that what we do is that we build when we want to take our object from when we want to take our data or the vertex data from what we had decided to the screen, we essentially do carry out a model transformation on it, a view transformation on it, and a projection transformation on it. So this entire calculation that we do, we multiply the vectors of that model with the model transformation, followed by the view transformation, followed by the projection transformation. When we do all of these three things, if you go back to our lecture 1 where we discussed what the graphics pipeline is, you would remember that we were multiplying our objects with the MVP matrix to get it to the screen, and this is exactly what we are multiplying it here with. So we start with the model transformation, we build a view transformation, we build a projection transformation. We multiply all of these together, and then we multiply it with each of the vector values inside the mesh to get the final coordinate of that mesh. Bear in mind, all of these three are happening continuously in your system. So if you are seeing a cube be getting animated on the screen, those 8 vertices are getting multiplied over and over again with the MVP. Essentially, what we're doing is we're just changing the values of these matrices. So when the value of the matrices change, the end result that you get change. And that's how animation gets carried onto your screen. When this happens 60 times in a second, you get a 60 FPS animation. You also might want to note that the M that we see here, the model transformation, essentially comes from the actual model or the world coordinates. This is typically done inside the 3D rendering program and the scene graph. So when you use a 3D rendering program to create a mesh, all the basic transformations or all the basic model transformations are in it, are done by the 3D program. Once that happens, when you load up the scene in your game editor or your gaming engine or your scene graph tree, you still apply a bit of transformations known as the world transformations, in which you basically specify where is your object going to be in the entire grand scheme of things. So the M really comes in from the structure of the object, or where essentially is that particular vertex inside that object. The V and P, which is the view and the projection, essentially come from the camera. These are typically done by all gaming engines under the hood, especially the projection matrix. This is all done. All these matrices are created inside the game engine by your game engine. You really don't have to worry about them. You only have to understand that these are going to be required when you're doing any kind of 3D programming. The view essentially defines wherein a camera is looking at a certain object from a certain angle. And essentially what happens is the camera is only going to return back the current view matrix and the current projection matrix to the system, and then it's your responsibility as a developer to pick up that matrix and apply it to your object. So once you do this over and over again for all your objects, your scene starts moving on the screen, and you start seeing things moving around. So imagine if there is a person walking on the road, or imagine if there is a if in your game you're making a car move on the road. What really happens is that all the vertices in those cars, or sorry, all the vertices in that car are being animated or are being run through this entire calculation every frame. And after those calculations happen, that is slammed onto the frame buffer, and the frame buffer starts showing things on the screen. So that's the basic that's the basic working of the graphics pipeline. Our job as programmers is to ensure to understand how these things work, and ensure that we are able to multiply our objects with the correct matrices like we want them to. You're going to be doing all of this inside the Vertex Shader, really. The pixel shader comes at a later stage. We'll talk about it, when we talk about colors, pixels, etc. But that is a subject for other discussion. Today we are going to be mostly looking at, how do you really multiply, how do you really calculate these, how do you really multiply these inside the Vertex Shader. And the Vertex Shader's primary responsibility is to do all of this to ensure that your vertex reaches the final values wherein it can be shown on the screen. So, like I mentioned, you do all of this here in this stage, and this is what Deep is going to show us today, wherein he's going to be creating an object, and he's going to be using that object he's going to get the vertices out of it, and he's going to start multiplying those vertices with his MVP matrix inside the Vertex Shader, and then stream all of it to the graphics card. Then it's the graphics card's responsibility to do all the tessellation, do all the pixel processing, and finally render it on the screen. So that's more or less what I really want to learn about the theory of transformations. So essentially, transformations are pretty simple. They're very basic. They are nothing but a matrix operation. Your data is always represented as a vector, or it's a zero rank tensor, or it's a single dimension matrix. It's a dimensional matrix. The transformation essentially is a multi-dimensional matrix. For a n-based coordinate system, you would typically use a transformational matrix that is n cross n in size. That's all you really need to know, theoretically about transformations, and that is really going to help you understand, that is going to really help you understand how you want to code, or how you want to code your Vertex Shader when you want to move things around, and B, that's really going to help you diagnose or debug problems when you see them on the screen. So, like I said in our last discussion, that debugging 3D can be really complicated, because you have to see things to be able to find out things, and the log is going to be your favorite friend. But if you really understand how those transformations are working, how those things are working under the hood, it's really going to make your life much easier. So I'm going to cut off here, and that's all the theory that we really need to understand about the transformations. And I'll move on to Videep, who's going to now take us through how do you build these transformations, how do you apply these transformations, and how do you actually start seeing the results in code. So thanks, guys, and I'll see you later. Videep, over to you.
Thank you, Girish sir. Thanks a lot, and hello everyone. I hope you are able to hear me now this time at least. Last time we had a bit of a glitch, and let us quickly open up Unity. So, if you would have attended one of the sessions at XRDI, we had seen a similar kind of a scene where I was actually explaining about what happens when you get a geometry inside Unity, and how it is all rendered. So let's quickly go through it once again. But before this, what I'm quickly going to do is I'm going to show you what is 3D geometry, as it was explained by Giri Sarwal. So the idea is to go into a 3D software here and quickly take a look at what 3D is. So whenever we are talking about creating games and all, the major part of the gaming engine is basically to get the assets, right, and then add the player and then start performing or interacting with the same. So if you see this 3D Studio Max screen right now that is present on this screen, I have two triangles here, right? Now, as we said that if you want to see a plane, we need three vertices, and if you go to any 3D software, it basically uh, will allow you to perform basic navigations and all, create meshes, create 3D. So let's understand about creating 3D first before we try and modify 3D. You know, to understand what's happening inside the vertex shader, where the transformations get applied, we need to first understand how this works. So let's say there is a 3D artist who actually has created a nice triangle here. The triangle, to make it appear as a mesh, it looks like an editable mesh in 3D Studio Max. Let's understand the basic stuff, where a mesh will be comprising of vertices, as we have already seen in the previous slides. It will be comprising of edges, so two vertices make an edge, and it will be comprising of faces. So the idea here is we have three basic things: the point, the line, and the face or the triangle. All right. So if we see, or if we could have gone to the previous session, we talked about lines and the primitives, right? So we have vertex, edge, and face. Now these three combined, right? These three combined give us an option to move this around, rotate this around, right, and scale it. Now this can be done in a 2D view or a 3D view. If you're familiar with 3D Studio Max, well and good. Otherwise, Blender, Maya, all these basic operations are allowed, right? But whenever you are doing this kind of transformation, how do you do it? So the idea is, even in Unity, uh, there is always a reference point called as a pivot. This pivot, or the handle, as Unity calls it, right? A handle, right? So the pivot allows you to grab these all vertices together, move, scale, or rotate whatever you want to do. You know, you can apply transformations, and these transformations are being applied runtime. That's why real time you see all these things, right? The idea is that whenever we are talking about the vertices with respect to the object's pivot, right, around which these vertices are created, we say that this vertex is in the object space. That said, the very smallest unit when we create a 3D mesh is vertex, a point in 3D space, a coordinate in 3D space. We should first understand that we can move the vertex however we feel like. We can move the edge, we can move the face, right? Now, when you do that, if you want to move the whole object together, you have to use the pivot. If you want to put the pivot to its center of the object, you can do that. If you want to move the pivot somewhere, you can easily do that. And that's what I'm going to show you, that in the second triangle, we have the pivot to the bottom center of this triangle. Now, why is this important? This is important because we need to understand the location of, or the position of this vertex with respect to the pivot, which we call the object space, right? The object space transformation of this specific vertex is going to depend on this pivot. Okay. So I hope this was very simple to understand, but now let's check this in Unity. So I have actually taken these to Unity, and here we go. So I got two triangles. One triangle is having the pivot at the center, the other one is having the pivot at the bottom center, right? And now let's inspect how these things work. So this specific triangle, when we get in the form of FBX into a gaming engine, right? I'm using Unity here. We have to understand what all components are applied to it by default. By default, we have a transform component. Okay, I'm going to just reset this. So this is the actual position of this triangle. It has a mesh filter. Now, if I remove the mesh filter, you are going to see that the mesh filter, is responsible to show the object or draw the object. And this mesh filter contains a lot of information. This is the link between the 3D objects and Unity, which makes Unity understand that what to draw, how to draw. Okay, basically what to draw. We have vertices, we have the index information for those vertices, but let's not go into that detail, right? We will just see it overall. After that, we have a mesh renderer. Now, this mesh renderer is very important because this contains a material. The material is an interface for a shader. It contains a shader. Now, this shader is eventually responsible to draw this mesh and show it on your screen. So, if I'm going to say that I don't have a material on this mesh, that there is no shader, the GPU is going to say, okay, the GPU will not say anything because this data is not going to GPU. There is no shader, it's not going to be drawn. Now let's take a look at this shader. Okay, so guys, if you want to quickly code this, well and good, guys, it's very simple. I can, let's start off with this. So I'm just going to create a new folder called, let's say, live coding. Guys, let's start off with creating a shader which is called an unlit shader, and I'm going to say vertex info. Okay, this is a very simple shader, and we call it vertex information. We create a material called as vertex information, and I'm just going to quickly drop the shader onto this vertex information, right? Now, the important thing is, considering this triangle, if I apply this material to this triangle, it turns white, right? Because the shader code is such. Now, I'm just quickly going to open this vertex information shader, and here you go. I hope the text is also readable. So what I'm going to do is delete all the code, right? Now we are going to delete the code, and let's start writing the shader from scratch. So as we know that to create a shader, we need a shader command which has a shader name, which is vertex info in our program, right? We are writing a vertex information shader, and it consists of some properties. We can eliminate this, or we can remove this from the previous session. You must have seen that how to create a very basic shader. Then you have a sub shader. Now this is important, right? And then you have a pass. So this is your basic skeleton, and if I'm going to apply this transition to Unity, you see that this shader still works, right? It has no properties, it has nothing, it just has a render queue and some properties that Unity just adds it to compile, right? Also, second thing that you might want to see is with this basic shader code, uh, it's not a surface shader. In its properties, it's not a surface shader. It shows a fixed function pipeline is being used. You can see the you can see the code, right? And a couple of other properties that we really don't care of at this point of time. Okay, we have not written any of the properties right now. That said, when we have this skeleton right here, okay, or the base code, we are seeing that our shader is already working, right? And it's using a fixed function or a default pipeline. All right. And if you don't add any of these, you're going to get pink magenta color saying that it's a shader error, and that is what we need to then debug. Okay, why we are getting that error? But let's start off with this. Continuing from the previous session, okay, we are going to quickly add a color. To write a property, we need to give the variable a name. It's called a color. We need to give a fancy name which the users can understand. So I'm just going to say color so that the user can quickly understand. And then we are supposed to write the type. So the type is color. Unity understands color, and this is going to be white color. All right. That's it. Or let's put it as a blue color. Okay. Now, with the basic shader pipeline that we had discussed earlier, right? So we'll start writing our code. So guys, you can just type and let me know if you are really writing this code, or if I can just quickly go through this very fast. All right, we can basically just quickly go through all these things super fast. All right, just 1 second. So we have a sub shader and we have a pass, and in that pass we start writing our basic. Okay, we can go through really fast. All right, perfect. So what I'm going to do is here we need a couple of structures. So basically we need a structure to get the information from the mesh renderer. Oh, sorry, the mesh builder. Remember the mesh builder, right? So from there, we just need to get that information. If you see here, we already have the structure right present. I'm just going to paste it right here. Then we need to create our own structure. So we can say actually I can just paste it here and I can say that it's a structure that we are going to pass it on to vertex to fragment shader. Then we create our own vertex shader. So you're going to say, how do you write a simple function? Void vertex shader. Sorry. Okay, it will not vertex function. Okay, it was supposed to be predefined. All right, and here we are going to take some data. Now, what data do we take in? We take app data that we are going to get from the GPU in terms of input. So I'm going to say input. Now, the output of this is going to be vertex to fragment, correct? So if you remember from the previous slides, we have vertex to fragment. So to return this, we need to initialize this output. Then we say, sorry. Now once this is initialized, we need to actually pass on the value, right? What value do we have to pass on? We have to pass on the vertex information. Now this vertex information is float 4. All right. So that means output dot vertex is equal to input dot vertex. Why is this like that? Because vertex getting from the app data right here in form of the input variable with a semantic of position. This is how the GPU is going to identify or map the variables, and hence when we create the output which is of type vertex to fragment, it has a vertex property and we can quickly pass it on. Once that is done, we need to write our own fragment shader, right? So when we write a fragment shader, fixed 4. So fixed 4, float 4, half 4, whatever you want to write, and just name the function whatever you want to write, right? So fragment function, and here I'm going to say I need to return a color, so I'm going to say return 1. Now this return 1 can also be written as fixed 4 like this, okay? So the GPU will actually understand. But how do we get this color? So you copy this, you say you want to use this color inside this pass, and how do you do it? Fixed 4, or if you want to go, so guys, fixed 4, half 4, float 4, 32-bit, 16-bit, 8-bit. All right, it's as simple as that. And you can say return this. This is a simple fragment function, but then if you were supposed to go back to the previous session, it was we need to provide a semantic, which is SV target. So you have to render it on a frame buffer, and this is how you do a simple vertex and fragment, where we have to understand the we have to specify that GPU please use this code, right? We have to basically say that the vertex function is going to be our vertex shader function right here on top of the, when you start off with the pass, and similarly the fragment function is supposed to be our fragment function, right? Now if I go here, oh, it's pink, that's great. So we have got some error in the shader. Now let's quickly debug. Set texture, okay. Wow, that's interesting. So let's quickly debug what did I do wrong. Let's get the console. When 12. Guys, can anybody? Oh, okay. Sorry. I have to say this thing again. Yep. Yeah. So guys, can anybody just quickly point out where we have to change this? Just a quick. Okay, perfect. We are not seeing the Unity editor. I think I just switched to Unity editor and then I switched back. Okay. All right. So guys, quickly tell me, where are we going wrong? All right. I won't waste much of your time here, but when we see this, see the shader code, right? We already understood that all this is to be compiled by just CG compiler, correct? That's why it is saying that we don't have a CG program. And it was expecting an CG. Now if I go to Unity and if I switch, perfect. So we have vertex information shader is not supported on this GPU. None of the sub-shaders fallbacks are suitable. Fragment program must be present in the shader snippet, excluding it from compilation. Unrecognized pragma directive word. Okay, that means we said this is the directive. Okay, guys. So this is very important. Why this is important is because you are going to get a lot of compilation errors when you're writing a first shader. Okay, so you have to be vigilant enough. All right. So here we go. Here we have the shader, and now this time if you see the shader properties, I hope the Unity editor is on. Yes, perfect, it is on. And if you see, we have the shader compiled. Perfect. You can all see the shader. Now what is happening here is basically we got the information. All right, we got the whole information, but it is not rendering because it's not getting the actual vertex data. Here is the actual play of transformations and vertices. So guys, now let's quickly dive into the transformations that we were talking about. At this point of time, all the transformations that we are getting as an input, sorry, I hope I'm on the right screen. Yes, are all in the object space. Okay, how do you know that they are all in the object space? Let's get back to Unity. Let's quickly take this shader. I'm going to select this material and apply it to the, here we go. All right. Now if you see right here, I'm going to put off the errors. For every triangle, I have basically added a script called vertex information script. This vertex information script is going to give me the position of the vertices. All right. This vertex information script is going to give me the position of the vertices. And now let's quickly check what the position of the vertices is. So if you can see, once I just switch on the script, enable the script, right? We have three vertices, one at 0, 0, 0.50. All right, so 0, 0.50, 1, 2, 3, 1, 2, 3, right? This is a triangle. Sorry. I'm so sorry. So the first one is like this here. I'm so sorry, guys. I'm so sorry. Let me focus on this. Yeah. So first one is 0 0.50. So 0 0.50 XYZ. This is the first vertex, second vertex, third vertex. Okay. Second one is 0.5. So x is 0.5, y is minus 0.5 and 0. And third one is minus 0.5 minus 0.50. So we have already seen this in one of the previous sessions, that how this works. We are getting this information from max. That means whenever we move this, transform this, I'm going to clear this out. If I reset it, I'm going to get the same information again. All right, just the same information again. We are having the vertex, the first vertex at 0.50, second vertex at 0.5 minus 0.5. In y we have gone minus 0.5, right? Because the pivot is right here. All right, and the third vertex being minus 0.5 x, minus 0.5 y, and 0 in z. 0 basically z, it has no what do you say, value. It's a 2D plane, right? So it will not have a z value. So it's all going to be 0. Okay, that said, we now know that wherever you take this triangle, the information of the vertex is going to be the same, and this information is already present in the mesh filter. Okay, which means we are taking all this information in the object space. Similarly, if I was supposed to close this script, go to the triangle which has the pivot at the bottom center. All right, if I'm going to have this at the bottom center, right? If I toggle the script, so where is the first vertex? 0, 1, 0, right? Second vertex, 0.5, 0, 0. So you see, this vertex is having the y position 0, because the pivot and y position of the pivot and y position of the vertex are at the same place. Whereas when you saw the previous triangle, for this, the second vertex had the y position as minus 0.5, right? Now this is very important, because here we have to understand that this is object space, as we are getting all the information for the vertices with respect to its pivot. With that said, let's look at the third vertex. It is at minus 0.5. So this is 0, assuming this is the pivot is the center, is what it is assuming, right? X is minus 0.5, y is 0 again, and z, of course, we don't have any value, right? Now that said, we have to dive into the vertex shader and ask the GPU to perform the matrix calculations. Okay, we are going to say, hey GPU, perform the matrix calculations in our custom shader. So this is our custom shader. We are not seeing anything at this point of time, right? Because all the values are in object space. So when I go to here we go. When I go to our vertex shader, right? This is the vertex shader function, right? All we need to do is we need to say multiply by model view projection matrix. Okay, this, if I just quickly go ahead and write, how do you perform multiplications? In shaders you have the multiply keyword mul, and if I just say unity matrix MVP, and I'm going to multiply every vertex with this MVP matrix, right? Let the shader compile. We have got this working. Alright, so we have got this perfectly working fine. Where the issue now is, we need to understand what is the difference between object space vertices, world space vertices, and we need to understand what is view space and what is clip space. Okay, so we are going to quickly go to Unity, and we are going to do this one by one. So first of all, M is equal to world space or model space. V is view, camera is the view from which you are viewing. P, projection, after it is being, after everything is being clamped onto the screen. For this, I'm going to go back to one of the slides, and I'm going to share the slides with you. If you see right here, okay, assuming this is our grid, this is our world, right? This is Unity, in which you have a grid, okay? wherever the origin of the world is 0, 0, 0, right? That is called the origin of that specific world. When I refer to the vertex information with respect to the pivot of this triangle, it is the object's vertices or the transformation set to be in object space. When I refer to the same vertices with respect to the world space or the world or the origin of the game engine, the vertices are going to be in the world space. When you put a camera here, assume that this coordinate is just a camera. Guys, whenever we are referring to a camera, it is just a point in 3D space. That fancy icon that we are getting is just a depiction of a camera, but it's just a 3D point in it's just a point in 3D space with XYZ coordinates. What adds on when you have to project is what I'm going to tell you later on. So when we talk about the position of this vertices with respect to the camera, we call it as in view space, eye space, view space. Okay, so view matrix. Then when you see this image right here, when we have a couple of objects, these objects are in a frustum, right? When we make a camera, we have to understand that we create a frustum because the camera is supposed to mimic the real life camera, all right, where you have a field of view. So you have a frustum, which is a six-sided box, but has a near plane and a far plane, all right, and this is controlled by the field of view. What happens is with the projection matrix, you multiply the vertices in such a way that all this is projected onto the screen, and the screen is the near plane. The near plane is called the screen. That's why whenever you go to the Unity camera, okay, if I was supposed to take you back to the Unity camera, whenever I consider this camera, your near plane cannot be 0. It cannot converge to a point. Whenever I do a 0, it will go back to 0.01. Okay, so that is the whole idea about this projection. Now this projection, right, if you see, when you apply this projection, right, you also have to be careful about what part of the object is within the clip space, okay, or is getting clipped or not, within the frustum or not. So when you project it back, okay, in this video, in this slide, we see that this part of the cube is clipped, only this part, and this part of the cylinder is clipped, right? Whereas the triangle is in full because the cylinder is being clipped by the far plane, the cube has been clipped by the side plane of the frustum. Okay, so you have six-sided box, okay, and that box has a near plane and a far plane, and that is controlled by the field of view. Talking about this, let's get back to Visual Studio, okay, and then from in Visual Studio, let's understand how this is multiplied for every vertex. So if I was supposed to say the type of this vertex is a float 4, right? So if I take a float 4 object position, okay, if I just create an object position and if I just provide this input.vertex, sorry, I'm so sorry. Okay, now I take this object position, this is an object space, to convert it into world space. I multiplied by Unity matrix M model, all right, model matrix. And instead of this, you might see a kind of a code change here. This is an automatic code change, guys. So I would just like to tell you that when I typed Unity matrix MVP and multiplied it by the vertex, the object space, Unity, what it did was it put an upgrade note saying that replaced multiply Unity matrix MVP with whatever your object space position is. It replaced it with this function because Unity provides that function by default. All right. So you have a function called object to clip position, which means you're converting the vertices from object space to clip space. That is why you are able to see the mesh or geometry. Now here, what I'm going to do is, I'm simply going to say output vertex, instead of this, I'm going to multiply it by view and projection. Okay, so what you do is you first take the world space, then in the output you multiply it by the view and projection, and it will be working fine, right? Instead of this, if you want to see how it looks in the world space, you just say world. Let's see how this looks. So let's go to Unity. Error. What's the error? Unexpected token equal to. Okay, where is the equal to? Let's transition back. Mistakes. Yep, we got an extra equal to here. So yeah, this is what you are getting to see right now, because the camera, the Unity does not have the information about the camera, right? And the information is not multiplied with the view matrix. So where is your triangle? You don't know where the triangle is, right? You got the information in the world space. World space is basically, you have multiplied this triangle by this position, the transformations, rotation scale. Okay, now you see this, it's assuming it's not multiplied with the camera, there is no view, and because there is no view, this is kind of an artifact that you're getting, because by default Unity would actually place the camera at 0 0 0. All right, so let's get something like this. Flip it. All right, now this does not have any of your what do you say, if I move it forward or backward, see, it does not have any of your projection matrices applied, it does not have any of your uh, field of view applied basically, so it looks pretty awkward, right? Here we go, that's the triangle, and you can move it around in world space, but with the respect of the view, because we don't have the view matrix, that is what we are getting. Then we say that, okay, let's multiply this by the view also, and I'm just going to say that take a new variable called view and multiply it by model in view, because first we have to multiply it by the model to get the model space vertices, then view, and I'm just going to say view. Okay, here is your triangle. Gone. Because it's not yet projected on the screen, right? There is no field of view applied to it, no camera clipping applied to it, nothing applied to it, right? So I'm going to put it back right there. I'm just going to reset it once. Go back to here, and this I'm going to say as your clip space. So MVP, okay, or if you want to just say that multiply the view space with the projection transforms, and I'm just going to say clip, and when you go to Unity, this is what you get. So now it's looking proper because your camera is placed right here, your object is with reference to the camera, and it is basically also applying these transformations. Okay, now one thing that we have to do is, let's enable, instead of returning some random color, right, let's enable coloring this by the position of the vertices. Okay, so I'm going to do a very simple thing here. I'm just going to, in the vertex to fragment structure that we have, I'm going to duplicate it twice or thrice, and I'm going to say this is the object space, right? So I'm going to say object space, world space, view space, clip space. Now guys, I'm going to change the semantics, because if you are referring this at the app data input stage as vertex, you cannot give the same semantic to all this, because GPU is going to get confused. Like, you're using position for vertex also, but in the next one you're mapping it to 4 different variables, whereas it should be mapped to only one variable. So there is a semantic called color. Now, because we are saving float 4 information, right, you can convert this XYZW WXYZ to RGBA. All right, so color, color 1 and color 2. If I go do this, what next I have to do is, I have to keep in mind to not let the structure be empty at any point of time, which means at this point I have to say output dot o object space is going to be my object position, world space, view space, clip space. All right, so world space position is going to be right here, clip space is going to be right here, no, view space is going to be right here, clip space is going to be right here. Now we have to remove this because there is no vertex variable here, but we have 4 variables. Now if I go to Unity, before I do that, I need to just tell you one thing, that this is the position, right? So this we cannot give as the object, okay, because position is very important. So let's put it to you can just put it like this. Okay, doesn't matter. Okay, so now position has been mapped properly, and let me quickly go to Unity. Wait 1 second. Transition. Okay. Unity. So we got all the spaces mapped properly. We can move it, and it's working fine. Now the next thing that we need to do is we will visualize this. All right. So to visualize this, what I'm going to do is I'm going to take some input. Now, what is the input going to be? The input is going to be the structure that we created, vertex to fragment. We initialized it. We added some values. This is going to be the structure. And if I say return input dot clip space. Okay, so in Unity we got some error. Now let's debug what the error is. Oh, this is a value. Oh, I did something wrong maybe. So what did I do wrong? Someone can tell me? Vertex to fragment input dot clip. Which is strange, which should work fine. Clip. Okay, there is nothing called as clip, guys. It's clip position. So if I transition now, here we go. This is the clip space, right? And what I've done is every time, okay, whatever the vertex information is going to, whatever the vertex is, we're going to provide it by the clip space, whatever is seeing on the projected on the screen. That said, we can quickly, like really quickly, transition into, let's see all the spaces. So first of all, we're going to check the object space. So if you see, whenever I map this vertices with the object space positions, right? I hope you understand one point here, that when I say mapping, I'm basically doing this. Fixed for color is equal to for RGB, right? So let's assume fixed or float r is equal to 1. I hope you already understood that how we are calculating the color. I'm sorry if I'm just putting this, but yeah. And if I just say color right here, what I'm doing is color dot RGBA is equal to input dot object position. Now this object position is float 4 or fixed 4, whatever I provided here is float 4. So it will get mapped to this, and when I go to Unity, this is the result, which means if I actually was supposed to say that guys, I want red color always to be 1. 1 second, I did the wrong thing. If I always wanted this red color always to be 1, I'm going to say color dot r is equal to 1, and here we go. So the red color is always going to be 1 full. Only the green and blue change based on the object space position. So you guys, if you remember, for the first triangle, for the first vertex, the object position is let me switch this on. What is the first vertex? First vertex is right here, RGB. So R is 0, G is 0.5, B is blue, 0. Then again, second vertex R is full because this is on 0.5. It's not full, it's 0.5. G is it's 0, basically -5 is 0, and B is 0. Alright, so you get a reddish color here, greenish color here. Why is the third color black? Because all of these are considered as 0 in the third vertex. Now that you have actually moved this, or you have asked the computer to just put the object position, let's see what happens if you put the world space. If you see the triangle in world space, right? It got compiled, and I'm going to say 0, 0, 0. Alright, so this is the 0, 0, 0 position. I'm going to put the camera a bit back. If you see right here, the moment I take this high up in the y-axis, all the vertices get colored green. So you notice I'm coloring this object in the fragment shader based on what? Based on the object, world space position of this. If I move it right, you see this is all red is going white, red is going 1, but here we have a bit of orange because y is also being present. And if I move it to 1, 1, right? See this. So this is called the object space. Now I can just move it to black, and yeah, if you want to see that, yes, Z value works, yes, it definitely works. Alright. So based on the position of the vertices in the world space, I'm coloring this object. It's now very clear and simple, right? And if I have to, let's say I have this cube and I'm going to apply this color here, you see how you get a shaded, nicely shaded cube with respect to the position of its vertices in the world space. Let's not dive deep into that, but let's check what happens when you transition to view space. So that's your view space, guys, based on the camera. Alright, now see, if I move the camera or if I move the object, both, because your world position is multiplied by the view position. Alright, that means, look at this difference, guys. I'm going to go back to the world space position. Now we're going to go to the world space, go to Unity. Alright, now this is in Z, and I'm just going to pull it up in Y. Now let's move the camera. So you see, guys, whenever we move the camera, there is no difference. Okay, what I'm going to do is I'm going to now view it with the view position. Now if you see the view position, object position is basically what we are getting from a 3D application, which is vertex position with reference to the pivot. World is basically with reference to the center or the origin of the world in 3D gaming engine. View is when you get the information, which is the object position, multiplied by world and view matrix, which means that's said and done. If I go to Unity, see how it just changes with the camera, right? Now it has nothing to do with the object space. Yes, it has something to do with the world space, okay, because this is world space multiplied by the camera view space. But you see this, how it is getting affected by the camera's look orientation as well. So this is the difference between, the positions of object space, world space, view space. Now if you were supposed to see the clip space, basically it's going to be yellow, because in the clip, after you get into the screen space, right, and you then put it to normalized device coordinates, until unless it's going out of the screen, nothing is going to happen. Okay. Now see this. All right. So this is how the clip space is going to affect it. We are going to dive deep into the clip space, but not now. Okay. For now, what I wanted you to understand is why these three spaces are important. Okay. I wanted to show you one more thing, but it might get a bit complex. Um, Let me know if it is getting a bit complex. I'm going to then move into more concepts of why we would use object space, why we use world space, why we use view space. I'm going to talk about that later. The idea here that I'm going to showcase to you guys is I have a blank scene, okay, in which I have a camera and I have a cube. This cube basically has a shader called transformations. Right now, if you must have seen when Girish sir, when they told about various matrices that we have, right? What happens when we talk about various matrices? We have a translation matrix, we have rotational matrix, we have scaling matrix. Every time in the vertex shader, the model matrix is a combination of translation matrix, uh, rotational matrix, and scaling matrix. And this is multiplied in a specific manner. Reason being, if you were supposed to rotate an object after translating it, the matrix multiplication is going to give you a very different result. So this is what exactly happens in a vertex shader. Now I have created personally these matrices in the shader itself, just to quickly show you how it is done. But these matrices can be created on the CPU, because whenever we are transferring information, oh sorry, I did not switch to Visual Studio. I'm so sorry. So yeah, just a quick look into the shader. In the vertex shader, this is basically what happens, right? We define the object space, like I told you. We define we define the world space. Object space is the one that we are receiving from the mesh filter. We define the view space, and then we do multiplied by the projection matrix, and that is the final result that we are going to portray or put it out. As Girish sir mentioned earlier, okay, we have a translation matrix defined like this. This is a column measure, okay. So that's why we have the last column as the translation matrix. So all the matrices are column measure. Scale matrix is defined like this. Very simple. Rotational matrices, we have three rotational matrices because one is rotation around the x-axis, one is rotation around the y-axis, one is rotation around the z-axis. And these three get multiplied these also have to be multiplied in a specific format. Okay. Not format, but in a specific order. Alright. That said, That said, let's quickly go into Unity and let me tell you about why we are looking into this. So in a vertex shader, okay, assuming what is the input? The input is object space vertices. Okay, I'm just going to talk about spaces now. So guys, uh, the input is object space vertices. For each vertex, all right, I'm going to define when I make this cube, right? For each vertex, I have defined the model space, the view space, and the projection matrix. Now let's quickly dive into what the model space is, the world space. So as we saw in the previous shader, we are getting input, which is the vertex information. We are providing this input to the fragment shader in a vertex to fragment shader, okay? And we are keeping the modified information here in this structure itself, so that this semantic called as SV position is going to go to the fragment shader saying that okay, we have this vertices placed here. The rasterizer is going to calculate all the vertices, all the pixels or the fragments as per the vertices in the clip space. Okay, now is the time to tweak. So guys, if you see in Unity right now, the actual cube is like this. Can you see the bounding box of the cube? The actual cube is like this, but in the camera we are seeing like this. The reason for this is very simple. The actual cube present here is being transformed to look like this within a shader itself. How? It's very simple, guys. First of all, we are taking all the vertices in the object space, convert and multiplying it with the world space. So if I was supposed to, in the translation matrix, right? This is a translation matrix, right? If I was supposed to say, I'm going to animate this. So in the y-axis, I'm going to say, now time variable is the one that you guys already know, that the time variable is basically uh, given by Unity. Okay, and if we do a sine time, we are going to get an animation. So if I jump back to Unity and if I hit the play button, you see it is moving in the y direction. All right, it is moving in the y direction, but the transformation is applied in the world space. Okay, so in the world space it is moving in the y direction. If I was supposed to quickly go here, all right, in this, if I just mark it as 0, right, and then I was supposed to put it in the view space. Let's see what happens. Now the transformational changes are happening in the view space. Okay, this camera here does not define the view. Do you see nothing changes if you go close? Why is it happening like this? Why the camera is not able to define this? Because like I mentioned, camera is nothing but just a set of matrices. Okay, if I was to say that I want the camera closer to the object, right, I'm just going to change this z value, go to Unity. Now we are closer to the object. Okay, field of view and all. See, if you change the field of view, only the skybox is getting affected but not the cube. Why? Because all these matrices that you see that are going behind the scenes in Unity, I have created right here. Okay, now understand. First of all, we are multiplying the vertices which are in object space to the world space. Then we are multiplying this with basically here, where is it? O dot vertex here. Okay, with the view space and the projection matrix, right? Once you do that, you have a perspective divide. Okay, so I'll explain the perspective divide as well to get the perspective of the object. Alright, so now if you look at the projection matrix right here, if I change the field of view, let's go down to 10, right? Now see, we changed the field of view and we went more inside the cube. If I was supposed to change the field of view to 50, can you see the distortion? But camera, guys, is again I want to make you understand, camera is just a 3D space, is just a 3D point in 3D space. All that happens with, you know, reference to the matrices. This is all mathematical calculation, guys. So tomorrow if you want to create your own geometry or your own gaming engine, you have to apply these matrices. So that's why if you see this right here, conversion into world space. Now assume I write a scaling matrix here in the world space. Alright. Can you see what's happening? It's getting scaled, but it's in the world space basically, right? In the world matrix. If I were supposed to do it right here, now you see how it gets, because it is y with reference to the view. When multiplied, the object is multiplied with the world and the view, the y direction is here. If I was supposed to do that for the x-axis, x-axis. Okay, so guys, I hope you really understand the difference between model space, view space, object space. Okay, if you have any questions, guys, please start writing down in the comment box. But also what I'm going to show you is to achieve this kind of output, which is not dependent on the camera. What I've done is I've overdone the projection matrix, okay, by providing certain parameters to the projection matrix. Alright, if you want some detailed information on the projection matrix and all the other matrices, please let me know. But the overall idea is, what is model matrix? Okay, it is translation into, alright, TRS, translation rotation scaling. Okay, now if you see the actual order, we are multiplying the vertex with the scaling first. We scale the vertex, we rotate the vertex, then we translate the vertex. Because as said by Girish earlier, whenever you're transforming a vertex, whenever you're rotating it, it is just a movement in a 3D space. It's not an actual rotation, correct? Similarly, view is basically same, but this is of the imaginary 3D coordinate called the camera. Now that is why I'm going to show you one more thing. Let's quickly switch to Unity, and I'm going to make this table first. So let's transition to Unity. This is working fine. Sorry, I actually changed that, but now you see in the code, whenever I'm translating the camera by 1, right, I'm asking the camera to move by 1 in the x-axis, right? You saw that instead of the camera moving like this, the object got moved in the opposite direction. So that is the whole idea about the cameras, guys. Whenever you have a camera or the view space, right, the transformations are applied in the inverse order. Okay, the transformations are applied in the inverse order. Alright, so that is the important part that we need to understand, that whenever we are transforming the object or the vertices in the view space, we have to understand that the camera, when the camera moves left, the object moves right. The camera is always assumed to be stationary. Okay, so guys, that said, we are converting from object to world, world to view, so that the object is represented inside the camera, and then we have a projection matrix. The projection matrix, okay, has a new function because it is not just multiplying. Here what we were doing is we were taking the translation, rotation, and scaling of that specific coordinate and multiplying it by the matrix provided by the object space. Then the camera is again a 3D coordinate, in the world, or in the, it's a 3D point in a coordinate space, in a coordinate system. But what is projection? Projection is much more than that. Projection is when you are removing one dimension. You're converting the data from 3D to 2D with respect to what? With respect to the width and height of the render window, the field of view. This is usually the horizontal field of view. Whenever you're constructing your own matrices, guys, please remember horizontal field of view versus vertical field of view. Okay, they both are different. Based on that, your calculations are going to change. And then this constant number is basically just the conversion from radians to degrees, right? Uh, so we have width of the window, render window, height of the render window. We have the field of view of the camera, and these two, guys, as you see, these two are the near plane and the far plane. It's as simple as that. So that is why this all contributes to the frustum and the aspect ratio. Then you get your uh, projection matrix created here. This is the projection matrix, how this looks. First row, second row, third row, fourth row, right? Your projection matrix. And that is how you finally convert your 3D object to a 2D space, and then you do a perspective divide. All right. So that is the idea behind getting, or what happens in the vertex shader. I hope it would be clear by now what happens in a vertex shader. Okay. These matrices, as I told you earlier, you have a flat scene graph. Okay. You can create these matrices and pass it on to the GPU. If you have a hierarchical scene graph, scene graph is if you have hierarchies of objects, okay, then it is considered optimal to calculate these matrices in the CPU itself. That said, you must have also understood that the object space is basically what we get from a 3D software, okay, or the software that creates 3D mesh, okay, or you can create it yourself as well, okay. The model space and the view space matrices, when do you need to calculate? So model space is basically with reference to your origin here. This is the origin 000. View space is with reference to your camera. And clip space. Clip space basically is the camera properties of near far clip box, which is right this. Okay, your near clip box, your far clip box, near plane, far plane, your aspect ratio, your viewport, and your field of view. Okay, that said and done, let's quickly go and understand that why these three spaces are important and when should we tweak objects and in what space. Guys, I would like you all to just take a quick 2-minute break and just let me know if you have any questions. But basic idea is object space conversions are important to world space, so that this object basically gets its information with respect to that world. That said, world space transformations are required to be multiplied with the camera space, because you have to understand if there is a camera animation. If there is no view space, right? If there is no view space, you cannot animate the camera. You cannot say that the camera should go closer to the object or far away from the object. So if I just want to create a 3D object, right here, all right. If I create a 3D object right here, this is the camera. So this kind of, the animation of camera moving, looking, rotating, or whatever, these kind of animations you won't be able to do if there is no view space matrix. And clip space is when you want to see this whole object rendered on a window. All right. Perfect. Now let's dive deep into transforming these. All right. So I'm going to create a new shader. Or let's utilize the same shader, like vertex information shader. We don't need it anymore. Okay, let's now transform this. So new scene, you have a camera. Now guys, whenever I'm going to ask you for a camera, there are two aspects of this. Tell me if I'm right or wrong. One, the view space matrix, and second one, view space matrix is this. Second one is your projection matrix. All right. I'm going to create a plane because the plane is going to have a lot of vertices in it. So 3D plane, reset, move it right here, rotate it. All right. That's your vertex information shader. And in the vertex information shader, what you want to do is you want to see the object space. That's your object space, guys. Every vertex is getting colored depending on where the vertex is with respect to the pivot. If you see this pivot, this is the center. So any vertex, any vertex that is below this point is going to be black, going into the z direction but not in the y, with respect to the pivot. Alright, it's with respect to the pivot. So I'm just going to say like this. I understand with respect to the pivot. So that's why we have black. This is a mixture of R is 0, G is 0, blue. This is G is 0, but R and B. So when you multiply red and blue, you get pink. And here we don't have any elevation. It's not going up in the y-axis. It's not in the z-axis. It's only in the right side. So we have this. Similarly, if I'm just going to see the transition of this with respect to the world, this is the world space. That means if I take it in the z-axis, completely z-axis, in your x-axis, right? You see that? With respect to the world, wherever the vertices are, you're going to get the color. Okay? That's it, and then we have visualized the various spaces, and third being the view space. So this is the view space. Now you see, when I'm rotating the viewport, how the information is getting changed. Isn't it cool, right? So this is with the respect to the camera. Okay, see here. Now let's transform these vertices. So when you transform these vertices, what we are going to do is we are going to transform the vertices in the object space, world space, and the view space. So let's go to the vertex information shader, transition it right here. Guys, whenever we are transforming the vertices, now you know that MVP multiplications take place in the vertex shader, correct? So I'm going to say in the fragment shader, we are just going to return a color. Okay, so let's say this color is what we're going to return, and we go to Unity and change this color to blue, cyan, yeah, right. And now look at this, guys. This is the most important thing that we need to understand via coding, and that is quick stuff. If I say the output position, okay, now understand this. Position is a semantic that the GPU will associate with when it has to consider rendering an object. Okay, if this position semantic is mapped with the clip position, okay, we are saying that in the vertex space, take this as the final output. This is the clipped position, take this as the final output. Rasterize based on the information provided in the clip space. Okay, so that's why it is rasterizing based on the clip space, and that information is provided to the fragment shader. Okay, so it's very important to understand what semantic we are using. So position is a semantic that is defined with the GPU for the position of that vertex that we are going to modify. Okay, that means whatever modifications we are going to do have to finally be put into the clip space by multiplying it by MVP matrix. Okay, so to make it very simple for you, what I'm going to do is I'm going to create a float for um, remember the object to clip position function that Unity, put a note here saying that we already have a function, guys. You don't need to multiply it by MVP matrix, right? So I'm going to use the same, and I'm going to give it an input as input dot. What is the semantic related with? Vertex, right? That's it. Your output position is going to be final vertex, and we're going to return the output. That's it. We observe no change, absolutely no change. Perfect. Now we are going to make modifications to this in the object space. How you do that? So you first take the object space. This is the object space position. Okay. Right now what we have defined it as input dot vertex. Correct. Now you take a sine wave example, guys. Okay, before going to sine wave, let's say I'm going to move this by 1 unit in the y-axis. Okay. After I move it in the y-axis, I have to provide this modified data. It's simple, right? You're creating a variable and you're providing it, right? Now you see here, your object has been modified and it has been moved by 1 unit. Okay. If I take the camera in the view, if you want to just see it, right? Where is the object currently? At 1 unit above the original object position. Okay. Similarly, if I was to say that, guys, I don't want to move this in the object space, but I want to move it in the world space. So I'm going to say world is equal to, okay, I want to copy and paste, multiply unity matrix world with object position. Whatever object position we're getting as input multiplied by the world, convert this world to +1, okay, and provide this here. But instead of providing it directly here, we don't need to multiply it by the world again, right? Because this is MVP. What we need to do is we need to multiply this by vertex and projection. Alright, this is your final. But there's not object position. Let me give the world position. That said, let's see if there's an error. No, there is no error. Now you see, this is what happens when you provide this in the world space. Okay, it's the same effect. Correct? But it is in the world space. Now let's see if we just want to give the height of just to give the height, right? What I was doing, I was adding it, whatever information we're getting from this, we just now if I just put it as 1. Now guys, you see wherever I move this, sorry, that was wrong. If I move this anywhere, it will move in x and z plane, but y-axis is uh, mapped, or it is, we have actually mapped it as 1. So even if I change the y-axis right here, the object moves, but in the view, because of the shader, it's still stuck at the same place. So what we're going to do, let's change it in the view space now. So the view is going to be multiply model view with the object position, right? We have the object position. For the world, we multiplied it with the view matrix. For the view, we multiplied with the world and view matrix. I'm going to say view.y is equal to 1. Let's go with +1 first. Bang. So now you get your, with respect to your camera, right? Perfect. And now let's stitch it to keep observing, guys. Alright, so it's not getting stuck here, because in the world space we have said that, guys, you have to take the world space also into consideration. If I would have said that don't take the world space into consideration, it would have never stuck up there. Okay. So that said, I am going to now change or add some more transformations. What transformations? The very famous sine wave transformation. Okay. In the object space, if I say, so when you have a sine wave, right? You have a sine wave going like this, right? You have a sine wave. What is the equation for a sine wave? Y is equal to sine of x. Simple. That means sine of that said, let's see what happens. Now I don't need the world space, I don't need the view space, I don't need any of these, I don't need this. You see, you got a sine wave right here. Now it's in object space. That means whenever you move this, y will always be the sign of x in the object space. Alright. So I'm going to change this to world space. World space, we get the world space, and in the world space, I'm going to say based on the world space position of this object, I'm going to get this information. So fine, we got an error here. Wow, what was that? World pose is undefined identifier. World pose, where is world? Okay, world pose नहीं है, world है guys. बता दिया करो यार. Transition, yeah. So now based on the, you see, based on the position of this in the world space, okay, but only x, right? It's only x. So if I was supposed to rotate it like this, you see how it behaves. So this is important because we need to understand, if we have a, like I had already told you in the previous session, like one of the sessions I had mentioned about the magic carpet, where what I was doing was I was just taking the object space transformations and basically just getting this in sine, and I was just multiplying it by time, right? So I was getting some kind of an animation here. Right? So if I just play this is the animation that you get when you multiply with the time, right? And this is in the object space. That means however you rotate this, all the transformations of the world space are going to be applied later on. Okay. That said, if I just go and put it right here, okay, I did not change it, right? I'm so sorry. I'm sorry. Yeah. So that said, how much ever you rotate it, right? How much ever you rotate the object, okay, it's going to apply transformations on the object itself, not based on the world position or the view or the camera position. It's not going to do that. Then just to make sure that what we're doing is right, I'm just going to say add the time here. Yeah, so that is the effect that I was talking about, a wave effect, but it does not get affected by wherever the object is in the world space. Now what happens when I do it in the world space? Do the same thing in the world space. I'm going to just comment this, and we need to comment this and comment this, right? So you get the world space. Now see, if the object is moving, the waves based on the world space are going to change. You see that? If I rotate it like this, the waves are going to change based on the world space, right? That said, let's do that in the view space. So I'm just going to say view is going to be like this. We don't care about the world space anymore. Just take the input whatever it is. View space.y is equal to sine of view.x plus time.w to make it faster. So just project it, right? We just need a projection for the view, correct? We don't need a, and bang, we got an error. Chalo ji, error kya hai? Use of unity MV is detected to transform a vertex into better performance. चलिए कहाँ गड़बड़ की हमने? नहीं यार, even that is not, we have done something wrong. Now what have we done wrong? We need to understand that. Guys, if you know what I've done wrong, just type it out. View space we are getting right here, which is multiply object this. Let's go one by one. Let's debug. Let's go one by one. What's happening? So if I apply this, yeah, it is working fine. View, basically we are getting the view matrix. But whenever we add this error, so let's say view.y plus equals 1. Now let's see what happens if I just go to transition here. So it's not stuck. It's fine. It's not stuck with reference to camera also. Yeah, it's all just fine. तो गड़बड़ कहाँ है? If I say one condition, it's gone. Bang. View space में it won't be visible, right? कहाँ गया? Is the flame gone? Right there somewhere. It's not been multiplied properly. It's just 1, right? So I say, oh, okay, all right. So here is the culprit. No, yeah. Oh yeah, guys. It was very simple. किसने लिखा नहीं YouTube पे, but it was very simple. This is time variable, yeah. It is not using underscore. Okay, so it has to use underscore. Now let's take save this and go to. So now, basically, this is dependent. You see, okay, I will show it to you like this. I'm taking the camera far. I'm taking the camera down. If I rotate the camera, do you see how it is getting transformed based on the view, or how the camera is, you know, rotated? You see that? You see that now it is just acting in a simple plane wave based on its relationship with the camera, how the camera is. Supposed to go close. See? I'll just take it closer. So this is what happens when you transform an object in the view space. A quick example here that I would like to tell you is, assume I have a capsule, right? I just create capsule in 3D. It's a 3D capsule, and I don't want to make my camera go a bit weird. Okay, so this is in view space, guys. You saw that, right? So forget about the plane now. Let's look at the capsule. Now when you take the capsule, and now I hope you must have understood about the differences, right? What happens when you change things in the world space, view space. How it is also important, the fragment shader. Okay, so I'll be closing off quickly with the fragment shader, guys. How is it important with the fragment shader is as simple as that. In the fragment shader, what I'm going to say is, if your object is, let me show you Unity and then I'll explain to you. If your object is at a specific location in the world, right? If it is going down, you make it invisible. If it is going up, you make it visible. Alright? That said, if I apply this, so here we don't need much information. All we need is the object space, world space, view space, position. So I'm just going to take this, I'm just going to delete this. We don't need this information. What all information do we have? We have the information of the object being in object space, world space, view space, clip space, all those 4 coordinate systems or spaces. You can say, you know, if you put the origin to the specific coordinate system, it will be a coordinate system will be same, but the space related to that. What do you say? That object or that specific coordinate. Okay, relative space. Okay, so now in here, where is our position mapped to C pose? Now our clips pose has to be unity object to clip position of what? We are multiplying the object space position with MVP matrix, providing it right here. Let's save it. Transition. To apply this to this, there is an error somehow. Not completely initialized. Nice. So when you say it's not completely initialized, that means W pose is here, V pose is here, object pose is there. Yeah, this has to be C, clip pose. Perfect. Now let's try some effect. All right, let's try some effect that we are going to continue in the next session. The effect is very simple. Now we know how this works. If I just return, that is how it works. RGBA, right? So I'm just going to keep it cyan. Let's go here. I'm going to say based on the world object space, guys. This effect I'm going to start off with the object space. So if I say if input dot, what do we have? Opos dot y, okay, is less than 0.5. I'm going to say take this color, put it into this variable, and then change this alpha value to 0. Otherwise, if it is greater than or equal to 0.5, you return whatever the color is. Before we go into Unity, I just wanted to say that we need to add a command saying that we discussed this in the earlier session. This command is very important. We need to add this command to make it transparent so that it considers the alpha value. Tags, we need to give some tags saying that what is going to be the render queue, okay, and the render type. So queue is supposed to be transparent, render type is supposed to be transparent. Keep it both the same. And yeah, let's take a look at what is happening in Unity. So in Unity, nothing happened. We got the render queue to be transparent. Transparency is working. So where the issue is basically is right here. When you are returning this underscore color, you should return this color. Okay, टोक दिया करो, बता दिया करो कि मैं कुछ गलत कर रहा हूँ. ठीक है? So tell me if I'm going wrong. Now guys, it's so cool. Wherever you go, wherever you go, wherever this object goes, based on the object position, we are clipping it. We have an alpha mask. Okay. Now you say that there is an issue here because it's not an issue, guys. You have to understand that we are taking object position into consideration, but we are not taking this position into consideration, right? The object vertices, there are no vertices in right here in this area. If there were vertices here, okay, it would have been different. And also, we are giving it a value which is basically saying 0.5 in the object space, which is from here. So whatever is getting rendered or placed above this position, okay, you render it out. That's why what we need to do is, as you considering that we are making these changes in the object space, we need to create a float variable here saying threshold of type float with a value of 1. This threshold we're going to copy it right here, say that this is going to be float. Can it is fixed also, not an issue. And here, now if you must have understood what we were talking about since a long time in the previous sessions, this is going to be the center. This is 0. So when I take it to 0, this is what 0 is. If I take it to -1, you see the whole object. So guys, this is very simple, right? Now I can rotate it however I feel like, and it is clipped. Okay. I can actually add a this we'll do later on. Basically, I can just quickly say cull off. I'm just saying cull off here, right? Transition right here. See, this is how it happens when you just do a cull off. You see kind of the back faces and all. Some of you don't want to do that right now. I'm just going to say don't cull, okay? Now, the next important thing is, I'm just going to show you one more important thing here. Now we took the object position, we'll take the world space position. So when you talk about the world, you see the whole object. Okay, so I'm just going to put a 0. If the position or of the vertex is, I'm just going to put the camera also right here, so that it is easier for us to understand, right? This is, where is the 0, 0, 0? This is the 0, 0, 0, the world origin, right? I'm going to create a simple 3D sphere. Sorry guys, I'm just taking some more time. This is the center. Now you see, whenever the object goes below 0, it is going to get clipped off. Okay, so if I rotate it also, if I rotate 90, bring up or down, it just gets clipped off at what position? 0. You can change it. And then you can actually do this as well with reference to the view. So now, if you're looking at from this point, right, see that? This is the camera's center. See the center plane of the camera? Actually not center, let me just quickly check. This is 0. This is the center. Yeah. So guys, this is quite about it for today, and why I wanted to show this to you and the clipping effect is because if you must have ever wondered about the craze that was going around the Half-Life games liquid shader, right? uh, Go take a look at all the videos and the demos that they have created. There are a lot of tutorials also on the web. Don't go through the tutorials, go through the idea that the creator applied, and then see why we discussed the transformational spaces are important. So that's the idea, guys. We want to discuss things so that we want to make sure you don't copy and paste the shaders, but you understand it. And now I hope if you have some basic understanding of object space versus world space, view space, clip space, that's great. That's great if you have that understanding. Please do write in your questions if you have any. I think we are done with the session for today. That's quite it, guys, for today. So if you have any questions, please let us know. Just start typing off in the comment box. Okay, guys, so I hope you have understood the difference between all these three spaces and why this is done in the vertex shader, right? What all is done in the vertex shader? Why is it done there? Why we don't do it in the fragment shader? It's very simple. The rasterizer will only rasterize the pixels in the and send it to the fragment shader in the rasterization stage, and whatever is in the clip space, the rasterizer will only consider that. Okay, so if you have understood it, guys, please just I would request you to type yes or no, so that I also get some idea if you have actually understood the concept of all these various spaces and the root of all the effects, the transformations, the MVP transformations. So do type it in the chat box, guys, if you have understood it. Okay, I think my YouTube got just updated recently, and yeah, I see Rudresh has replied about the underscore thing. Thanks, yeah, Rudresh. Thanks a lot for joining. I mean, it's lovely to see you here. Thanks, Mani. Thanks a lot, Manikandan. Thank you. So, thank you all, guys. If you have any questions, do throw it. We will respond the questions soon. And also, we wanted to say that let me show you the Half-Life liquid shader that we are going to talk about soon. There's a channel called Polygon, and I'm going to share the screen right now. If you see this channel called Polygon, right? Yeah. Here it is. So I'm going to show it here. So this I would always expect, or I would always say that go through this
We're all taking up
channels so that you understand the
painting.
idea behind this.
Below.
Okay. So guys, if you see this liquid shader, it's basically changing or clipping things in the object space or with reference to a plane, right? So go through this kind of video, understand how it is done, try to replicate it. I would love if you can replicate this kind of an effect yourself. And also we are planning to have some kind of coffee meetups where bring your own coffee and shaders. Basically every Sunday, we're planning from next Sunday onwards. uh, every Sunday you bring your own shaders, you ask your own questions, you have any effects that you want to ask, do ask us. And going forth in the next boot camp, we will start off with writing practical shaders, guys. We are going to write practical shaders. We are going to do, we are going to understand why it is important to write your own shaders, how you can write, uh, basically create an effect by understanding it. All right. So Girish sir, you want to add anything to it?
Yeah, I just want to thank everyone. Can you hear me? Can you guys hear me?
Yes sir. Yes sir.
Yeah, I just want to thank everyone. Can you hear me? Can you guys hear me?
Yes sir. Yes sir. Okay, I think I should mute myself.
Sorry for that feedback. I just want to thank everyone, and I would urge all of you to keep a watch on our meetup group and on our YouTube channel. So we hope to do some cool meetings going ahead. We're also planning to, like Vidip mentioned, we're also planning to change the format a little bit so that we can bring best of the content for you. And very soon, I will be sharing a feedback form with you. I would really request all of you to fill it because that really helps us improving these sessions. So thanks, guys. Thank you very much.
Thank you all. Thanks for being here. Do drop in your comments if you liked it, if you understood it. Thanks a lot. And thank you, sir. Thank you, sir, for explaining all the awesome transformations. That was great.